I'm delighted to welcome back to the department Zach Espiritu. Uh, 4 years ago, he received his bachelor and master's degrees in computer science, and he is currently at MongoDB working as a research engineer. I feel personally very fortunate to have collaborated with Zach in multiple dimensions. So he was had TAs repeatedly for CS 166, and he also has been part of my research group, as well as also he collaborated also with Sani Kamara and worked in addition with Shrira. And he received numerous awards for both his research and contributions to our TA program, including the Norman Meyerowitz Award, which we give not every year. It's only when we have exceptionally deserving students, and also the Randy Pausch Award. Zach is working in an industry research lab with several, Brown alums and former faculty and postdocs, and is going to talk today about this work on attacks on searchable encryption, which is also the subject of a paper he will present at the IEEE Security and Privacy Conference next month. Zach.
Thank you for the very kind introduction. So as Roberto said, I was last here at Brown as a student 4.5 years ago. So I'm very excited to be back. It's been 4.5 years since I gave a talk about research in the CIT, which was on my very first paper with Roberto and Lalika, which was also on encrypted search, but in a different context. So I'm excited to present something that is related to that. I'm also excited about this paper, particularly to present it at this specific venue for a few reasons. One reason is that this paper is not really a theory paper. Depending on which of my reviewers you ask, it's not sometimes clear where exactly this paper falls. But I really like it for this reason. There's a bunch of different things that I'm interested in research, for better or for worse, if you ask my collaborators. And this is like one of those exciting papers where a little bit of everything I like kind of appears. So I hope that you all find something interesting in this that you like as well. So as Roberto said, I work at MongoDB. MongoDB is a database company, so let me give you a simplified model of a database as all of these kinds of talks start. You have some client who has some data who wants to outsource it to some remote server of some kind. I'm a cryptographer, so I think of ways that you can use cryptography to improve the security guarantees of this kind of simplified deployment, usually in terms of confidentiality. One particular kind of threat that we're considering primarily in this particular setting is one where we have an adversary that is able to somehow compromise the server in some particular way. This motivates solutions for what we'll call encryption in use or encrypted databases, where essentially we want to try to design some kind of database scheme that uses cryptography such that the data is end-to-end encrypted from when it leaves the client and it is stored on the server. But providing confidentiality guarantees on this data is sort of in tension with our desires to also have reasonably efficient sublinear search over this data. And so, but I don't think I need to convince you all of why, even in spite of this challenge, this is still important. You know, if you look in the news, there's many different incidents of data breaches and data compromise events that basically show that, there are real threats to data that it's outsourced to these databases, and so we really do want to try to come up with nice solutions for protecting data in this end-to-end encrypted way, because it can directly mitigate these kinds of threats. And so cryptographers have spent a long time kind of thinking about how you might implement this through various different primitives. These are just some primitives that you can use. These primitives on the screen in particular have been pretty extensively studied, both in terms of their trade-offs, in terms of security and performance and functionality. But there's one primitive that has not seen as much attention, specifically from a cryptanalysis perspective. The title of this paper kind of gives it away. It's a trusted execution environment-based encrypted databases. A trusted execution environment is essentially this hardware-backed primitive for confidential code in memory. There's a few examples of this on the screen. You don't really need to know exactly how they work, but the claim that they usually give to you is that even in the presence of a persistent, powerful, potentially even physical adversary that gains access to the host machine, it will provide confidentiality guarantees over all of the code and memory that is stored inside of the TE. All of the programs and algorithms that you put inside this TE are going to be confidential in some way. And so from a security standpoint, this sounds very appealing. From a design standpoint, this is also really appealing, assuming that the TE is secure. You can imagine many different ways of using this primitive to simplify your encrypted database designs. And these tools are so mature and developed to the point that you can essentially take any existing program and just shove it inside of a TE. So early deployments of TEs were primarily memory limited, but that's no longer really the case anymore. So now you have what we call TE native systems, where you essentially run an entire custom DBMS inside of a trusted execution environment, or even what we'll focus on in this talk, lift and shift systems, where you take any existing plain text database and you just put it inside of a TE. And there are many papers that literally just do this and propose these as encrypted database constructions. There's even companies that commercialize these exact deployments. Like, we'll give you an end-to-end encrypted database, but really what they do is they just take Postgres or SQLite and just stick it inside of a TE. And so from as a cryptographer who's trying to design encrypted databases, it's natural to ask, like, if this primitive really does work in the way that it's described, then maybe this is actually kind of nice for us. It simplifies a lot of our design, and it gives us very strong security guarantees. Of course, relying on this big assumption at the top, that the TE is secure. And if you spent any time at any top-tier security conference in the last several years, there's at least one paper at every one of those conferences which shows that through various kinds of side channel attacks, you can basically break this confidentiality guarantee. Now, you don't need to know specifically how these attacks work. The unifying thread between all of these attacks is that they generally rely on some kind of persistent adversary model. You need to either physically get access to the host machine, or you need to have the ability to run a program on the machine that's co-located with the victim program over some long period of time. Essentially, you need to compromise in some persistent way the compute-related portions of the host machine that this database is running on. Now, here's the turn. In our experience deploying encrypted databases at MongoDB and talking with different customers, and also looking at the literature on industrially deployed encrypted databases, the reality is that a lot of customers, not all, but a lot of customers don't really care that much about this persistent adversary model. The reason for this is that when you look at the class of threats that generally affect database deployments in the real world, they usually don't emerge from persistent compromise of the compute portions of the machine, and rather they're the result of much simpler compromise models. For example, a database administrator's accounts get compromised, or a backup account that holds backup files of the database gets compromised. We can loosely call these, this class of adversaries, something that we'll call snapshot adversaries. There's different kinds of ways that you can define what a snapshot adversary works. One particular example that I want to highlight is from 2019. There's this Capital One data breach incident where Capital One is storing encrypted customer databases inside of Amazon S3, which is this remote file system. You can think of it essentially as that. And so you have servers that are running databases and then periodically sending backups to some Amazon S3 storage layer. And the adversary in this particular scenario was able to compromise credentials to these S3 buckets and then repeatedly read the database files over and over again. And so here you can view this as kind of a storage snapshot adversary, or what I'll call an external memory snapshot adversary, where the adversary is only able to periodically read point-in-time snapshots of the database across the execution. But they're not compromising anything in the compute layer. And in this TEE deployment model, this is kind of interesting, because if you really look at what portion of the database or of the server that the trusted execution environment is protecting, it's really just protecting this compute layer at the top. Of course, you can apply some encryption to files before you send them down to the storage layer, but the traditional threat model for trusted execution environments considers this file system or storage layer, or however you want to abstract it, outside of the trusted region of the TEE. So even if we're in a world where we don't know of any general attacks against TEEs that work in a non-persistent model, and we can assume that it has perfect confidentiality guarantees over all of the code that's in memory, you still might leak some significant information down here. And this is really important for persistent databases, because the reality is that after every single transaction that happens, in order to have strong resiliency guarantees, it has to necessarily write something to the storage layer. So the interaction between the TEE and the storage layer is something that is really important and has not really actually been explored that much in prior work. So in this work, we basically want to ask, with all these different observations that we've made about TEEs and what's protected and what's not protected, is it possible for someone to take one of these TEE-based encrypted databases and infer some non-trivial information about the data that's stored inside of it? So we'll formalize this capital 1 example into this model that we'll call this multi-snapshot external memory model, where after every single transaction on the database, which we'll say is just an insertion for right now, the database will process that insertion and then write some encrypted file to the storage layer. And the adversary, this snapshot model, sees a snapshot of the disk after every single operation. It doesn't see reads. It doesn't see individual write system calls. It just sees snapshots of the file. So after every single operation. Mm-hmm. We'll assume that there's some kind of atomicity guarantees here, that there's no partial writes to this. So after the transaction fully completes, you just see a single snapshot. Mm-hmm.
So we're saying that this kind of attack is not as much explored, but I remember seeing like memory access leakage from TEE.
Yes.
And people have proposed using ORAM and stuff.
Yes.
To protect that. Is it related, or this is completely different?
So the memory access patterns are what I'll call internal memory attacks, and they usually require you to have some kind of persistent access. So you can, the ways that you can see the internal memory accesses usually require some ability to compromise this compute portion, which I was talking about before.
But also because a lot of the TEs have limited memory, so if
Mm-hmm.
they wanted a lot of memory, then they would necessarily require this outside storage. So then there is this.
Yeah. So most of the ORAM memory protection frameworks, they only protect the internal memory of the program. There are some works on external memory ORAM, and that's something that I'll mention again later. But they are distinct for some papers. Mm-hmm. Yeah.
If you have an EDBMS that something can guarantee history-free of the operation, in the sense that whether you do add or you do something that leaves the state of the database in a way that's independent of the operation.
Mm-hmm.
Well, the snapshot model here, like that help?
Like if you're able to.
Yeah, like you take your
Mhm.
EDBMS, it's history-free.
Mm-hmm.
And then you just do this plugin, as you mentioned, where you encrypt everything, store it.
Yeah. Let's talk towards the end again about like what you might do to mitigate some of the things that we do here. Mm-hmm. So in this model, we're trying to figure out how you might learn something. So we'll make a sequence of observations about what you can possibly do. The first observation is that when files are written out to disk, they're not just blobs of data. They're usually structured in some way, primarily because the existing database is trying to have sublinear I/O and efficient accesses to disk. In particular, we'll consider like a B+ tree data structure that this encrypted file is representing. And also, in order to have efficient I/O, this data structure is page aligned with the file system in some way. Now, in many file encryption mechanisms, including those that are inside of trusted execution environments, these are also page aligned in some way. So what this specifically means is that when a update happens to a particular page, that page is updated in the encrypted file, but all the other adjacent pages to it are not updated. So if you have a bunch of snapshots of the files on disk, and you take their diffs, you can see the set of encrypted file system blocks that get updated after each of these operations. And so our idea basically is that if we can see the set of encrypted file system blocks get updated after every single operation, maybe we can reconstruct some information about the underlying B+ tree in the database. Okay? So this is what we're going to show in this talk. We're going to say that if you have this multi-snapshot adversary that records all of the snapshots, we'll first reconstruct something about the B+ tree layout. And then from there, we'll show that you can recover some approximate ordering information about each of the insertion operations. So I can tell you the record 1 is less than or equal to record 2, for example. And then from there, we'll do some stuff that's very similar to inference attacks on property preserving encryption, where we'll actually take that ordering reconstruction and tell you what the exact plaintext values are, or the approximate plaintext values are. Okay. There's some simplifications that we'll make. First is that we'll just consider only single record insertions. There's no deletion operations. We're also going to make this kind of strong assumption, which is that the adversary sees the snapshots after every insertion from the inception of the database. At the end of the talk, though, I'll briefly mention some stuff about how you might try to relax this, or both of these. The other thing that we'll do is that in our paper, we concretely focus on one particular instantiation. So we focus on a SQLite database that's running inside of a TEE using this Gramming wrapper. Yes?
So here, the file encryption module does not change the structure that it received from the storage engine?
I'll show you in a second. OK. So I'm going to go over the attack now at this point. One thing that I want to emphasize is that you don't need to know anything about TEs, really. And you also don't need to really know anything about cryptography. This entire attack is going to just be a sequence of almost trivial observations about the data structures that will then compound together in some interesting way. So as a very high level preliminary, I just want to recap B+ trees. B+ trees are just a search tree that maps keys to values that contains some capacity M keys. This M is very large so that it's aligned with the pages in a file system. You don't need to know exactly how these parameters are set. Just know that it's a search tree. When you search in this tree, you look at the root, which contains some divider keys, which tell you the boundaries of each of the children. So for example, if I want to search for k equals 10, I look at my divider keys, and I know that I have to go to the node that contains elements between 8 and 14. And so on. You do the same thing for insertions. You do a search, and then you insert the value. So this insertion observation is important because every time I see an insertion on my database, I know that it's going to be translated onto a set of writes on this underlying B+ tree structure that this file is representing. We also had this other observation that the logical database pages are structured so that they're aligned with the file system page size or block size. And as we just had a question on, there's this file encryption layer that provides some kind of translation between these plain text blocks of the storage engine and the encrypted blocks. Like there's some mapping between when a plain text block gets updated, which encrypted blocks get updated. Now, you don't need to know exactly how this file encryption mechanism works. In many trusted execution environments, there's this very complicated Merkle tree kind of structure that's also trying to provide integrity guarantees. But the important thing to note here is that this transformation between the plain text blocks and the encrypted blocks is deterministic, primarily because the file encryption mechanism is still trying to preserve some notion of sublinear random page accesses to different pages on disk. And so when I update a particular page, for example, if I update plain text page 3, as we'll call it, I can always tell you that encrypted blocks 7, 8, and 9 will always get updated. There's this deterministic mapping between the plain text structure of the file and which encrypted file system blocks actually get updated. So, yes?
That are part of the index versus the final pages where the data is, do they have all the same size, or you have like the internal nodes on the
All of the nodes are in the B+ tree are the same size.
same?
Mhm. So this observation of the determinism allows us to construct what we call these inversion functions, where essentially, if you consider the encrypted delta, or the set of encrypted file system blocks that are updated by a given operation, you can write some inversion function that lets you reconstruct the set of logical plain text database pages that were updated by that particular insertion. If you look at our paper, we have some inversion function for the Rabbit. But the point is that because of this determinism, I can tell you, given any particular set of encrypted file system blocks that get updated at a given operation, I can tell you exactly which plain text database pages are going to be were updated by that particular operation. So the advantage of looking at of doing this mapping and looking at this mapping between the encrypted file system blocks and the plain text blocks is that now, when I'm trying to figure out how I might reconstruct the B+ tree, I just have to think about the behavior of B+ tree updates in terms of what updates would be happening in the plain text setting. I don't have to actually think about the file encryption mechanism at all. Now, I still don't actually know the plain text of these pages. I can't see inside of them, but I do know like the plain text page identifiers that would be updated by a given operation. Okay? So here's what you might be able to do with this. Let's suppose that we knew what the index tree structure looked like, so we know how the plain text page numbers map to the particular actual logical structure of the B+ tree. If I have two operations and I see that they only touch these particular set of leaf nodes, so operation 1 touches leaf node 6, operation 2 touches leaf node 12, because of the fact that the B+ tree indexes things from smallest to largest values, I know because of the fact that 6 is to the left of page 12 that the value inserted by operation 1 must necessarily be less than or equal to the value inserted by operation 2. So if I can recover the B+ tree structure, and I can also tell you which plain text pages each operation touched, I can then essentially repeat this observation over and over again to learn the ordering relationships between each of the inserted records. Okay? So there's a bit of a gotcha in SQLite. So in all plain text databases, there's usually not just one B+ tree. There's actually multiple B+ trees. So there's an index tree, which is the thing that we have been talking about, which actually maps index values in sorted order to record IDs. And then there's a record tree, which actually maps the record IDs to the actual records that are stored, to the actual full records that correspond to that record ID. Now, unfortunately for us, in SQLite, even in the plain text setting, the index files actually interleaves all of these B+ trees together. So when I see a particular delta, I see a bunch of plain text page IDs that got updated, but a priori, I actually don't know which tree each of these IDs actually belongs to. And so it makes it kind of very difficult to reason about like what's going on. You know, maybe it's easy to reason about one B+ tree in isolation, but I don't even know which B+ trees each of these pages belongs to up front. So in the paper, we solved this by doing this, coming up with this technique that we call disambiguation, which essentially asks for each page that we see, which tree does it belong to? Does it belong to the index tree, which is the thing that we care about, or does it belong to the record tree? So here's an example. What I'll say first is that there is a known base case. So we know always that page 1 is going to be the root node of the record tree, and page 2 is going to be the root node of the index tree. But then after that, we don't know anything. So what we're going to do is we're going to leverage certain properties of SQLite B+ tree algorithms, which we do by direct inspection of some of the code and by doing some other reasoning about B+ trees in general, to try to figure out how we can actually disambiguate these nodes. So one nice property about SQLite is that when a new node gets added or allocated at some point during the execution, the node never switches between the tree that it was originally assigned to. So if page 8 is a new node that appears in some operation, if we somehow know which tree that it belongs to at the point that it is created, I never have to think about it ever again. I know exactly which tree it belongs to. So at the time that each new node is introduced, all I have to do is decide which tree does it belong to. So if I know that it belongs to the index tree, then I know for the rest of the transcript's execution that it's always going to be in the index tree. Of course, you still need to figure out exactly which tree that it belongs to. So there's a really trivial observation about B+ trees that you can leverage in order to actually figure this out. And it relies on the fact that the parent nodes contain pointers to the children. If 8 wasn't added to the index tree, it also necessarily means that its parent, 2, must also be part of the updated set of pages in that particular operation, because its parent must now have a new child pointer to page 8. And so we formalize this through this very silly named lemma that we call parental presence at inception. Basically, if P is a new node that's introduced by a particular operation, then its parent must be inside of the delta. And this is not very useful on its own, because what happens if it doesn't, the conditional is actually in the wrong direction. But if we take the contrapositive of this is actually more interesting. If no possible parent from a given tree is in the delta, then we can conclude that P cannot possibly have been added to that tree. So in this example, if we know that 1 is the only possible root for the record tree, and 1 does not appear in the delta, then we can conclude that 8 must necessarily have been added to the index tree. Okay? And this is this really trivial observation, but it actually handles like 95% of all of the new nodes that we see in a given workload. Yes?
Can you remind me what is delta again? Is this a path?
Delta is the set of plain text pages, database pages that have been updated by a given operation.
So it's like all the nodes of the path that goes to
Yes.
leaf page.
Yes. Not necessarily all of not all of the nodes on the path necessarily get updated. Yeah. If it only needs to update like leaf nodes, it will only update leaf nodes. Yes.
Think about the data structure as you insert records. At some point, the root will need to split.
Yes.
And then a new root gets created.
Mm-hmm.
But you only do insertion. So what happens to those nodes?
So splits do happen, splits to greater levels. I'm going to elide that for right now. You'll see it again in a second. This point about the tree increasing in height and how that conditionally complicates things does add significant complications actually for this disambiguation problem, because then the set of possible roots, the set of possible parents, starts to expand. We actually can handle this. But this is one of these edge cases for this disambiguation problem that we need to handle in the paper. I will defer this entirely to the paper, but I'm going to claim that there is a lot of stuff that you can do and reason about the B++ tree algorithms, and eventually you can come up with this provable way of actually doing disambiguation. So you end up coming up with this very tiny algorithm, which is actually quite nice, but requires a lot of nice machinery to do this disambiguation. But I'll talk about splits again later on. But the point is that you can provably work out which nodes belong to which tree. And so now this is quite nice, because now we only have to think about the rest of the algorithm in terms of one tree in isolation. One other reason why I'm kind of eliding over this disambiguation part a bit is that in this work we focused on SQLite, where we actually have to focus on this problem. But in other databases, you actually don't have to do disambiguation, because in other databases, different B plus trees are actually stored in separate files. So if we extend this attack to some other databases, which we have done, you actually don't need to do any of this work at all. You actually are given the B plus tree nodes separated a priori. Okay. So we're left with the set of nodes that are now index nodes. And so now what we want to do is we want to figure out the structure of the B plus tree. And actually, if you think back to our warm-up a bit, where we learned the order relationship between two records, we didn't actually care anything about the higher level structure of the tree. All we care about is the order of the leaf nodes next to each other. So we'll actually simplify our B plus tree reconstruction problem a bit by instead trying to reconstruct just the order of the leaf nodes in the tree. So we'll split this up into a few parts. First, we're going to figure out which one of these nodes are leaf nodes. So we'll disambiguate the internal nodes of the tree from the leaf nodes. And then later on, we're going to reconstruct their order. You can also reason, to do this part, to figure out which nodes are leaf nodes, you can also reason about how the B plus tree algorithm works and the traversal algorithm in SQLite and how it interacts with some of the page allocation mechanisms in SQLite. So here's an example that illustrates how you can potentially figure this out. So let's say that there's a set of new nodes that gets added in a particular operation. And once again, we know that all of these nodes are index nodes. Because of the fact that SQLite B plus tree algorithms use a depth-first traversal, where when you do an insertion, you traverse all the way down to the bottom of the tree, handle doing insertions, and then traverse back up, and then handle any adjustments you need to make at higher levels of the tree. If a new node gets added, it always has to necessarily be, if multiple nodes get added, the first node that gets allocated is always going to be at the lowest level of the tree, or it will be lower than all other nodes, and that other new nodes that have been allocated in the tree. So in this example, we've allocated a new node. The first node gets added as a leaf node. This might cause another new node to get allocated at some higher internal level of the tree. But the point is that this allocation ordering is also visible in the page indexes in the plaintext page, in the plaintext database page numbering. So the fact that I can see page 9 and page 10 get added, I know that page 9 has to have been a new node that's allocated at a lower level of the tree than page 10. So we have some additional machinery in the paper that essentially allows us to recover, to disambiguate the internal nodes of the tree from just the leaves. If you look at this lemma carefully, there is an edge case here. There's an at most one new node is a leaf, which means that it's possible that none of these are leaves, actually. And we'll tell you that in the vast majority of cases, it is a leaf. And in the paper, we have some machinery to handle the case in which, so what we're going to do is we're just going to assume, for example, that the minimum node is always going to be a leaf. And then later on, we might find out that it actually wasn't a leaf, but we have some additional machinery to be able to handle this. So if you're interested in how that works, I would direct you to the paper. Yes?
Ordering
Mm-hmm.
depends also on the way you implement it. You
Yep.
figure out everything that you require, and then
Mm-hmm.
the order.
Yes. So this is a recurring reviewer question on this paper. One response is that our observation is that, well, it doesn't. So it's just interesting because of the fact that it doesn't do this, so we can't exploit it. The other thing is that it's actually not trivial to change the ordering of this allocation because of how the storage engines need to handle concurrency. So you could imagine some reordering of the pages, but it actually might be very expensive to implement. And there are known documented works on implementing B plus trees that talk about this. Another thing is that even though let's imagine a world where you are able to somehow reorder the allocation of these pages, I still think you will get enough information that you can create more complicated constraints, essentially, to reconstruct the structure. Okay. So using this lemma, we're able to take all of our nodes that belong to the index tree, and then we extract out just the leaves. Okay. So the rest of the final step that we have to do is figure out what the ordering of these leaves are. And this follows from how B+ trees handle splits. So if I have an insertion in a B+ tree, and I find out that there's no space in the node that I'm trying to add the new key to, what I could imagine doing is just splitting this node into a lower level, and splitting this node into 2 nodes, and then making this a new parent. But this will increase the height of the tree, perhaps unnecessarily. So what many databases do, including SQLite, is they do a local rotation of keys that involved in the overflowed node, where they rebalance the node with its adjacent neighbors. So in the middle node that got rebalanced, it looks at its 2 neighbors, and then it essentially reallocates all of the keys across those nodes in order to avoid doing a split unnecessarily. And then if this process still would overflow, then it finally allocates a new node. Okay? But the important thing about this rebalance optimization is that it leaks the locality of the nodes of the leaf nodes in the tree. So if I see a rebalance operation, for example, if an insertion rebalances pages 1, 4, and 5, I know that pages 1, 4, and 5 have to necessarily be next to each other in the structure. SQLite also has an additional optimization where the way that it assigns the final layout of all of the pages in the rebalance operation is in sorted order based off the actual page numbers. So you actually learn even stronger information than just the fact that you don't learn that 1, 4, and 5 are next to each other. You learn that 1 comes before 4, comes before 5. Though, for Roberto's sake, even if it didn't tell you the exact ordering, you could do some like PQ tree kind of stuff to be able to figure out the ordering. But the point is that this rebalance optimization gives you a significant amount of locality that lets you reconstruct the ordering of the leaves in the tree. So this brings us to our final step of the reconstructuring portion of our attack. Essentially, our idea is as follows, and we'll actually we'll kill 2 birds with 1 stone in this step. So we'll not just reconstruct the leaf ordering, but we'll also tell you which operations land in each particular leaf. So what we'll do is we'll maintain some linked list structure that represents the ordering of the leaf nodes at a particular step of the operation. If we ever see an operation that only touches 1 leaf node, then we know that that operation's inserted value must have fallen inside of that leaf node. Now, we don't know exactly where in that leaf node it landed, but we just know that it's somewhere in that node. So we'll just maintain a set of all the operations, all the operation identifiers that land in a particular node. If we ever see an operation that touches multiple leaf pages at once, we know that it must have been a rebalance operation because there's no other situations when this happens. And so what we'll do is we'll add the operation to any of those nodes, and then we'll simulate the rebalance operation. We'll reorder the pages according to the ordering constraint that we just learned from the fact that the rebalance occurred, and then we'll also reorganize the operation identifiers accordingly. Okay? And so when you do this, you get something that looks like this. So these green dots represent operations, okay? And here I'm just showing you the rebalance, the deltas that involve the rebalance. I've removed deltas that only touch 1 leaf node. And so you can see here, from the shape of what's happening on screen, that these rebalance operations basically allow you to reconstruct the exact ordering of the tree from left to right. And so we look at which operations touch each page, and then we move them accordingly. And then if we keep following this process to the very end, we end up with the order of the leaf nodes, and then we know approximately which operations are inside of each of those leaf nodes. And that allows us to get the approximate order at the end. I'm going to pause here to let this marinate, but if anyone has any questions, please feel free to ask. This is on a real workload, by the way. This is not fake rebalances. This is on one of the experiments that I'll show. Okay. So at this point, you iterate over the leaf structure, you concatenate all of the operation identifiers in the order, and then you just get some approximate ordering, right? And then if you're familiar with the literature on inference attacks on property preserving encryption, what you do next is very natural. If the adversary has some auxiliary information, like a histogram about what the insertion value should be, they can use the quantile function of this auxiliary distribution, and then you kind of just rotate it outside, and you map the order that you get onto the surface of this histogram, and then from there you get back the actual plain text values. Okay. As a remark, this is not exactly the same as other attacks on property preserving encryption, because order revealing encryption also leaks frequencies. It also leaks equality information. Here we don't have any equality information. We just get orders. So we kind of basically have to just take this histogram for granted. So as you'll see in some of the experiments that I'll show, if your auxiliary information is not good, if it's not really close to the actual thing, you'll get some bad results. Okay, so here's the first case study. Here I'm generating 1 million random, this is on a synthetic data set where I generate 1 million random insertions from a set of 1-byte integers. This is a uniformly sampled at random. So 1-byte integers is 256 possible values from negative 128 to 127. And here I'm plotting every insertion. Every dot is one insertion. And then the x value is the guessed value, and the y value is the actual value of that insertion. And so the diagonal is better. It means you guessed it exactly correct. One thing to pay attention to is the color. So purple points are operations that appear early in the transcript, and yellow dots are operations that appear later in the transcript. You'll notice this kind of interesting phenomenon where the early operations are very spread out. Like we don't really know exactly, we don't really have good information about them. But then as we get to later in the transcript, we get almost perfect guesses for a lot of the insertions. And you can visualize this in a different way. Here, I'm plotting error. By error, I'm going to take the difference between the guess and the actual value. And then I'm just going to plot it on the x-axis, which is the order in which it appears in the transcript. And so here you see, at the very beginning of the transcript, the error for each of the insertions is very high, but then it converges towards the midline, which means that we get good guesses. Yes?
Do you have to make these guesses as you make the query, or?
No, we make our guesses all at the end. Yeah. I'll talk about why this is the case in a second. Yeah, we make our guesses entirely at the end. I can concretely give you some numbers here. So e-recovery just tells you the percentage of points where we exactly get the guess and the actual equal to each other. I've divided it up into quantiles. So Q1 is the first quarter of the transcript, Q2 is the second quarter, and so on. So you can see that this gets better over time. There's this absolute average error metric. Absolute error is just the guess minus the actual, the absolute value of it, divided by the domain. So this is error sort of normalized as the size of the domain. As you can see, the error decreases over time. To get to Peihan's question as to like why does it look like this? The intuition is that early on in the transcript, the B plus tree is very small. So for example, here I only have 3 leaf nodes. If I tell you which leaf node a given operation lands in, I can tell you its rank with respect to 33% of the domain in this case. But later on in the transcript, if I have sort of like n leaf pages, I can tell you, and I tell you which operation, which leaf page a given operation lands in. There I'm telling you, for which 1 over n part of the domain that operations actually landed in. And so essentially, as you get later in the transcript, the longer the adversary is able to execute their attack, the more specific ordering information it's able to recover about each of the XIs.
But you cannot infer information about every transfer from there.
Yes.
Assume later on you also operate on top of the initial transfer.
Yeah. So the reason also is that the boundaries of like each of these pages, like the minimum and the lower, the the lowest and highest values in each of the pages is changing over time. So even though like I know, for example, that an operation lands in this page, that same page, which could be somewhere in here, its boundary has changed later in the transcript. But I also, because I don't actually know like how the rebalances operations have like moved a given operation in a page, I don't actually know if that operation is in the same page. So that's information I only learn for operations later that appears like at the very end of the transcript. So the fact that I can't see exactly where rebalance operations are moving operations is the reason why you get this behavior where things that happen early, I don't really know exactly where the operations are moved, but later on I can. Any questions?
This seems like it's kind of statistical. So the attack result is statistical. Is there any way we can like show more confidence?
Like can we like bounds what the error is like whatever as a function of like the transcript size and the domain size or something like that?
I guess my question is just that can we get better results if we somehow by just increasing the amount of compute we any way to
by compute, do you mean increasing the transcript index or by
just like given the current leakage, can we
So
use more compute to get better?
if there are additional constraints that we have not identified in how the databases work, then yes, probably. But we have not found those, at least not publicly. But talk to me after.
I guess one could do better if you could inject values.
Mm-hmm.
Because then you will have
Yes.
more precise.
Yes. I'll talk about one other way that you can do better after one more experiment. So here's another experiment. This is on a very small domain. This is on Amazon's 5-star reviews. So there's only 5 possible values that you can get. Okay. And we have some other results in our paper, which are that on really small domains, you get really good recovery because the fact that you don't know the exact ordering of the records is not impacted as much as when you have a larger domain. But here you can see this kind of interesting phenomenon where in one of our Amazon data sets, the reconstruction quality gets better over time, but then on the other Amazon data set, it actually gets worse over time. And you can see, if you look at the cumulative distribution function of each of these data sets, the real data set is the solid blue line, and the auxiliary data set is the dashed line. And you can see in this example, the auxiliary data set that we use here is actually quite far off from the actual distribution. And so essentially, this is one example in which, because of the fact that we only have order leakage, if our auxiliary information is not quite right, we cannot do better. Now, if we had frequency information, if we had some way of recovering the histogram, you could adjust the histogram to make it better. If I finish my paper tonight, you'll see how. Okay, in the last 4 minutes, I want to say one really important thing about this paper. I think it's probably the most important thing about this paper that is not really well captured in this talk so far. And it all kind of stems from this one big lie that I've kind of been telling you about this work. It's a lie that I've been telling you from the very first slide of this talk, from the title of the talk, which is that when you really look at what's going on in this paper, none of this is really specific to trusted execution environments at all, right? I mean, yes, this is the reason why we looked at this talk, and our attack actually does work concretely against this trusted execution environment-based database. But when you look at the diagram, the flow of information through this, through the TE, and we're calling the diagram that we showed earlier, there's nothing really specific about the fact that we have these TE lines here that is affecting what's going on with the attack. The thing that we're really exploiting is that the database has some IO optimized external memory data structure, that then is, deterministically encrypted by this file encryption mechanism. And we also have this scenario where it's reasonable to assume a world where you can independently compromise the storage. So there's other scenarios in which this thing is actually kind of interesting. So one scenario in which this is interesting is that if you actually look at how real cloud deployments work, often these remote VMs that you're instantiating, they're actually not really just one VM. The compute layer is physically distinct from the storage layer. So there you could just imagine a world in which you deploy an encrypted database, but the adversary, for whatever configuration reasons or however the infrastructure is being managed, the adversary is only ever able to compromise just the storage layer. And so here, this attack would work. Another thing that's also interesting is that there's this emerging class of databases that's called disaggregated databases, where it's not even that the VM that your database is running on is physically separated, but the compute layer and the storage layer and the memory are actually instantiated as completely separate VMs, potentially in completely separate clouds. And so there's even another example that's even easier to see, where an adversary who maybe only compromises one cloud is only able to see either something that's happening on the storage layer, something that's happening on the compute layer. And so we've been looking at applications of this work to these kinds of emerging databases. And because of the way that these databases also do some kind of encryption, we think that there's also some nice applications of this attack to those places. And I'm sure there will be more interesting things that you can come up with different kinds of compromise models in this setting. Okay, so to recap, we have this attack that lets you recover stuff from the database by looking at snapshots over time. There's a bunch of limitations that I mentioned right at the beginning. Like there's this assumption on the workload. We have to see snapshots from the very beginning. So we would like to say, is it possible to relax some of those assumptions? Once again, if I submit my paper tonight, I'll be able to answer at least some of those questions. The other thing that also I think is interesting is from a mitigation perspective, this goes back to Peihan's question earlier. We could kind of just throw ORAM at this, you could say, and maybe everything is solved. There's some weaker versions of ORAM which are interesting for this specific threat model. For example, write-only ORAM, which only protects the writes. And that actually gives you some better efficiency guarantees and actually aligns very nicely with how databases work in practice, where when you do writes, you have this kind of periodic checkpointing process where you're OK with the database getting slower during the process of doing those writes. So it might be possible to come up with some co-designed write-only ORAM that works well with the storage engine to mitigate at least this specific kind of attack in a reasonably performant way. Of course, you could also hyper-optimize ORAM if you wanted to just apply it in general. There's also this question that I talked about before, which is can you extract more leakage? But if you're interested in that, you can talk to me after this talk. But I'll stop there. Yeah.
Questions. I think that might be a little bit related to Roberto's question earlier about the reordering. I was wondering, it seems like part of this assumes that in some sense you can invert whatever functions that's used to go from the file encryption module to storage.
Yes.
I was wondering, can you potentially use something like a seed to scramble initial, the starting points?
Mm-hmm.
That way, maybe because of that, you don't exactly know what sort of arrangement space you are working
Yeah.
with.
It's a bit challenging because the file necessarily has to kind of grow over time. So I could imagine a construction where I allocate a bunch of space in a file, and then I kind of randomly put some pages, and then I maybe double the size of that file over time. But that's something that would be sort of very different from existing file encryption mechanisms. For the most part, they work in this kind of way where they're designed so that you can add a new page just one by one over time, because they're trying to minimize storage overhead to be exactly the size of the actual plaintext file. But there's trade-offs that you can make in this space. You can also do what some papers do in this space, which is like just throw ORAM on the file system or something like that.
Since it was 5 by 5, what if you pick a permutation per file?
A permutation per file?
Yeah.
Well, when you need to add just one page, like what do you do at that point? Do you
When if there's still space in the file, then
Yeah.
since you have a permutation, you want to add. But if the file is full, you pick a new permutation for it. Right?
Yeah. So you could do some kind of like rebuilding process where you like allocate more space and then reshuffle pages around during that, something like that. I haven't seen anything like that, but if you're interested, we can talk about that.
About mitigation. So one is, you mentioned the deterministic file encryption system.
Yeah.
I'm wondering if it's not deterministic, but like somehow keyed by key, is it?
Yeah, so I think this is the same question. I think there's no schemes that I'm aware of that do this, but I can imagine a world where maybe if you're okay with allocating more space than you need up front, that you could do some permutation of the pages, something like that. Yeah.
The other thing was, you mentioned the internal memory might be ORAM. So
Mhm.
if the internal memory is ORAM, does it help with external storage? Because then it's like
Well, it requires the external memory to also be ORAM. Yeah. Yeah. Yeah, there's a lot of work that only focus on ORAM at the internal memory. There's some that do both, and then there's some that only do external memory. But yeah, if it's only an internal memory, at least my understanding is that you would still see the logical ordering of the plaintext pages in the file. But maybe I'm not thinking of something, so we can talk about it more.
I was thinking of ORAM, but you have limited memory space. So then, like the external storage is just expansion of the storage.
Yeah, so there's
ORAM is still
there's some like resizability thing that you need to solve in the external memory model, because in the internal memory, you're right. You can reasonably have some bound and on the ORAM and just get to steady state right away. But yeah, in the external memory state, because of the fact that you have to kind of keep increasing the size of the file, it's not immediately clear how you do it. I am not sure exactly how the external memory structures work off the top of my head, but yeah, there's something there. Yeah, but I know that resizability is something that is not really well studied in the ORAM setting. Like essentially what you do, I think, is outside the context of any particular memory instantiation, you basically do a rebuild where you just double the size of your ORAM and you just copy everything into the new one. So there's probably some work to be done there.
Does the adversary need his snapshots to be consecutive?
Does it need to know the order? Is that what you're asking?
Yeah.
Yeah. So here we do need to know the order. Well, do you? I mean, you can get order from the lengths of the snapshots, if that makes sense.
Okay.
So the order is kind of implicit in some of them. Yeah, I mean, the one way in which it would hurt the evaluation is that we're trying to assign exact record identifiers, like record 1 landed in this page and record 2 landed in this page. So if you don't know the exact order of the snapshot, it's not clear how you assign like a given record ID to the given insertion. But yeah, in theory, you could probably still do the reconstruction of the B+ tree if you wanted to, even if your snapshots were in a different order. Yeah. Mm-hmm.
And so
Like some history independence of some kind?
Yeah, it's
Yeah, yeah, yeah.
That help?
Yeah, so
Where-
we have some mention of this, so we didn't look into it in too much detail. Basically, we made this connection between breach-resistant structured encryption schemes that are like snapshot secure and breach-resistant structured encryption schemes basically use like techniques from history independence. So it's possible that if you have, you can take some techniques from history independence and just come up with a scheme that will solve your problems here. But it's, you know, once again, this kind of growth of the file, I think, might impact you. Yeah, it's not clear. Maybe Roberto, you know more about this.
Those are very, very interesting over programs. Well, looking at that with my definition and the interplay between history independence and the social English. Yeah, there are
Are there like similar notions of like snapshot security and history independent data structures? Yeah. Okay. Yeah. 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 Anything else?
Thank you.
Okay.